So questions from the homework from last day. And also, we're probably going to get about halfway through the next lesson. We'll finish off the lesson Thursday, and Friday is kind of a weird short day thingy, so I'm not quite sure how all of that's going to work. Anyways, number 4, find the acceleration of the dragster. Okay, I'm going to draw a free body diagram. Actually, let's move it over so I have more room. There. Hey, Michael, what are the forces acting on the dragster? Get the obvious one. Darn right. Is the dragster sinking into the ground? No. Is it flying into the air? No. Then I think vertically my forces are balanced. I think vertically there has to be a normal force up. What else? Which way? Now, you are correct, and this is where a lot of students make a mistake. See, a lot of students will say, well, Mr. Dueck, there should be an applied force pushing the dragster forwards. No. What force pushes cars forwards? Friction. Friction. The only horizontal force is that. That's it. Who's winning? Friction. Who's losing? It's a trick question. No one. My equation, Michael, is going to look like this. Friction equals my net force, and my net force is always just plain old MA. Friction is what times what? Well, friction is mu times the normal force. I don't know the normal force. Oh, but look. On my free body diagram, I know another force the same size as the normal force. What? What did you say we're trying to find? How to get the A by itself. And it turns out when I divide by the mass, actually it turns out the mass cancels. It turns out that the acceleration of a dragster does not depend on its mass. It only depends on how sticky its tires are. That's a bit of a fib. We are technically ignoring some air resistance, although our dragster is fairly aerodynamic. So some air resistance, but not much. You know what? The acceleration is going to be 0.8 times 9.8, which is 7.84, I'm pretty sure. By the way, do you see why I said this question is so simple that it's tough? It's so simple that there's really only one horizontal force, but kids want to put more than one there. They want their, and I've seen even teachers say, oh, there's an applied force, the engine to the right, and friction to the left. No. If the engine is what made your dragster go forward, then if you put a dragster on ice, since that engine is still there, it should be able to go forward, and it doesn't. So what force has changed? Friction. Friction must be what makes the dragster go forwards. Is that okay, sir? Yep. Any others besides number 6? Number 7? What was yours? 5? 5, very, very similar to number 4. Okay? There is no number 7. That was a joke. I'll joke you. Wait till you see your next mark. 5 says this. A 50-kilogram rollerblader moving at 3 meters per second drags the foot on the ground. What are they asking me to find in number 5? You know what? Since I happen to have it here, let's do number 5 down here, because I think I'm going to need a little more room. Yoink. And apparently my dictionary doesn't know the word rollerblader. That's okay. What did you say they're asking me to find at number 5? Okay. I think I like number 5. I think I like number 5. I think I like number 5. And what I mean by that is we're going to use, well, you'll see. I'll tell you what I like in a second. Well, what else have they told me? Which velocity? VI is 3. What else have they told me? What's VF? Oh, it says stopped? Yes? What else do I need if I want to find distance? Well, either time or acceleration. Are we doing forces? You know what? Valoria, even though this question said find distance, I'm going to spend far more of my time finding acceleration. And that's what I like about this question. On your forces test, you can absolutely expect a Unit 1 question like this, where I don't tell you the acceleration. You have to use forces to find the acceleration. That I like, because it's also great review. We've done a couple of those. You're going to see some on your take-home quiz, your next one. I think there was some on your first take-home quiz, too, for that matter. How can I find the acceleration? Forces. You know what that means? This is a job for a free body diagram. There's the rollerblader. What are the forces acting on this rollerblader? Get the obvious one. Gravity. Is this rollerblader sinking into the ground? Is this rollerblader lifting in the... Nope, nope, okay. What else? What direction is the acceleration of this rollerblader? To the left, slowing down, and we've decided that we'll always have things move to the right unless the question specifically says different. That way, Jeff, all our diagrams will look the same, and I don't need to always tell you that in the question. So slowing down, there has to be a force that way. Which force is that? That's the dragging foot friction. Is there a force to the right? What force? Speed? That's a velocity. That's meters per second. I'm not putting force. That's not in newtons. The only things that go on my free body diagram are newtons. Is there a force to the right? No. Do you remember a couple of days ago in our lesson, we talked about the shopping cart on gravel. And we said, when you push a shopping cart, yes, it comes to a stop because there is a force acting in the opposite direction of motion. Even though it's moving forwards, Jake, there is no force pushing it forwards. Velocity is different from force. Velocity is different from acceleration. This is the free body diagram. In fact, it's almost like Michael's dragster question, except in the dragster question, friction was causing us to accelerate forwards. Here, friction is causing us to accelerate backwards. And so on that note, who's winning? Friction. Who's losing? It's a trick question. No one. You know what? On that note, I think friction, which is the only force, winner minus loser equals ma. You know what? The rest of this is going to be exactly like this. We would then say, friction is mu times the normal force. I don't know the normal force. Look, 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 look. There's another force the same size as the normal force. And so we're going to end up with, I think, mu mg equals ma. I think we're going to end up with a equaling mu g. Which, by the way, is the acceleration anytime you're trying to stop a car or stop anything from rolling by dragging something or applying the brakes. It's 9.8 times whatever the coefficient of friction is. Oh, 0.6 times 9.8. 0.6 times 9.8, 5.88. Which we'll put in the acceleration now over here. Hey, what's the equation that has distance, initial velocity, final velocity, and acceleration in it? Oh, it's the VF squared, VI squared one, and you actually got the D by itself? Well, thank you, I appreciate that. You said, hey, Mr. Dueck, it's VF squared minus VI squared all over 2A. It's 0 squared minus 3 squared all over 2. By the way, I've made a mistake on purpose. Can anybody see the very subtle mistake that I've made on purpose? Ben?
When you put in all the numbers, you actually went VI squared minus VS squared.
No, I'm good so far, I think.
Oh,
Nice try. I've made a very subtle mistake. The nice thing is I did it on purpose because we're going to note it. Do you see it? Yeah. Nope. Nope. Okay, let's keep going. We're going to catch the mistake because we've learned enough physics to recognize strange answers. Type that in. What do you get? Sorry, what? Type it in. You really and truly want to type that in. You'll notice a strange looking answer. You'll notice something weird about your answer. What? Oh, you get a negative distance. Say what? Why? What was my subtle mistake?
You didn't put those negatives through that bracket.
No. No. Michael, what? Okay, we've been deciding to let positive be whatever's convenient in the forces unit, and I hope I've convinced you why that's so much handier. But last unit, if you were slowing down, the nice thing is, though, if you forgot that, Anthony, hopefully you would spot on your calculator. That's a little strange. Oh, and if you have a good calculator, hopefully I've gone on a rant about the importance of getting a good calculator, you can probably just backspace and put a negative in front of the acceleration. Anyways, the magnitude is correct. What'd you get for a distance? Sorry? 0.765 meters. Is that okay? That's going to lead us actually to number 6, which I said was sort of a bonus. Number 6 has parts of this question and other stuff as well. Oh, that's a problem. Do that, Mr. Dueck. Where's number 6? There it is. Clip. Sally right now is in my Physics 12, and she can tell you that I actually assigned this to my Physics 12s. So I'm sneaking in some Physics 12 here. You guys are good. I don't like the instructions in this question. The question says, describe the motion of the block. That's too vague. I would never give that. So what I did is I looked at the answers, Trevor, and I said, okay, it looks like they want V final after the first 10 meters. That's what that 4.9 meters per second is. Oh, and then it looks like they want distance in the next chunk. So I broke this question in half. I like this question in terms of the physics. I don't like the way that it's worded, so I'm not saying I like this question, I like this question, I like this question. I do like the two-partedness of it. So Darian, I glanced at the answer that they wrote, and I said, oh, I guess they want me to find that. Oh, looks like I traveled 10 meters, the first 10 meters which are frictionless. There's another thing. I have to assume that we start at rest. I don't like that this question makes me assume that. That's another reason, Emma, why this would never make it on a test for me. I'd like to find V final. I don't have enough. What else could I use if I wanted to find V final? I think even though this question is saying find the final velocity, I'm probably going to spend a fair bit of time finding acceleration. And what I want you to realize, this is why acceleration is so handy. We now have 5 ways to find acceleration because it showed up in VF equals VI plus AT. It showed up in D equals VIT plus a half AT squared. It showed up in VF squared equals VI squared plus 2AD. And, 4 ways. And it shows up in F equals MA, free body diagram, winner minus loser. And there's more. But the fact that we have multiple ways means we can move from method to method it allows us to tie both of these units, both of these topics together quite nicely. You said a free body diagram? Okay. I think we have gravity down, normal force up. It says we're pushing with 60 newtons. There's my applied force. And it says the first 10 meters are frictionless, so no friction. Vertically, everything's in balance. Horizontally, who's winning? The 60. Who's losing? It's a trick question. You know what? 60 equals ma. I think A is going to be 60 divided by the mass. 60 divided by 50, 1.2 meters per second squared. Forwards, so positive. And now, to find V final, I could use Vf squared equals Vi squared plus 2AD, although to get rid of the Vf squared, square root. Okay, Atla, you asked me this one? Who asked me number 6? Yeah, so I'll let you take that part on your own. I'm going to move to the after. I'm going to set both of these up, and then I'll let you take it the rest of the way yourself if you want to. After, it appears, looking at the answer, that they want us to find how far. And I have to assume it comes to a stop. Why? Well, the answer says then stops. So V final is 0. V initial is whatever answer that you get from there is going to be V initial. Right? I do like that part of it. I do like a two-part question where a final in step 1 becomes your initial value in step 2. I do like that. Oh, you know what, Atla, even though this question says find distance, I think, much like before, I'm going to be finding acceleration. How? There's a job for a good free body diagram. Let's see. Gravity down, normal force up, pushing with 60 newtons to the right, friction slowing it down. Why did I draw friction so much bigger than the 60? I think it's winning. Has to be because it's slowing down. In other words, what's my equation? If I go winner minus loser equals ma, what minus what equals ma? Yep. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force on my free body diagram. Which one? Hello? Which one? Yeah, mg. So you're saying mu mg minus 60 equals, and Atla, I'm going to get the a by itself. I'll divide by m right now. That's, I think, should give you the acceleration that would go there. And then, again, just like Valoria's question earlier, you can use vf squared equals vi squared plus 2a. You can use d equals vf squared minus, you can use this here. And you should be good to go. Oh, you're slowing down. You probably will have to actually say to yourself, this acceleration is going to be negative, even though I'll get a positive answer when I go winner minus loser, because I've let the negative be the winner, because it was easier for math. Okay. Now, if you haven't finished the questions from lesson 4, you're probably in luck. I'm going to go most of this class starting the next lesson, but I'm not going to finish it, I don't think, unless I'm going much faster than I anticipate. So we're going to continue on. Lesson 5. We're nearly done, forces. Very quickly, can you look at the take-home quiz, the first thing that I gave you? Forces quiz number 2. Okay. Number 1, there's probably 2 words that I would underline in number 1. Everybody see what 2 words that I would focus on? Yeah? That's constant speed, because if it's a constant speed, I think your acceleration is 0, which changes your equation. What's this question asking you to find? What's mu? I don't know. What's mu with you? It's not asking you to find friction, by the way. Friction's the force. It's asking you to find the coefficient of friction, which is mu. Number 2, we're free falling. What direction do you accelerate when you're in free fall? Down. Which way is air resistance in my free body diagram then? Up. When you do a free body diagram, gravity down, I think air resistance up. No normal force, you're not on a surface or anything like that, and I think you can go winner minus loser and you'll be okay. I want you to find the acceleration. Number 3. Number 3 is asking you to find the net force. Net force is ma. So I think all you're trying to do in number 3 is find the acceleration, which I think is going to be all unit 1 kinematics, VIT at half AT squared, VF equals, all those ones, and then just go ma. No need for a fancy schmancy free body diagram, because if I'm asking for the net force, I've taken care of all of friction and all that stuff. Number 4, what are they asking you to find in number 4? Number 4, what are they asking you to find? VF. How many marks is it worth, Kai?
3.
You know what? This is actually kind of similar to what we've just done going over some of the homework, where even though they're asking you to find VF, I bet you're going to spend most of your time finding the acceleration with a good free body diagram. You can use that, right? Number 5, Mr. Dueck, who drew that picture? Why, I did. Thank you. I'm so glad you noticed. I'm pretty proud of that one there. So in number 5, they're asking you to find the acceleration. Here we have friction, and we have a force with ski poles. You'll have to think about this one a little bit. 3 marks, enough said. Number 6, again, there's probably 2 words that I would underline if I were you. But in this case, instead of asking you to find mu, I'm asking you to find what force is required to keep it going at a steady speed. Meanwhile, tuck that away. Lesson 5. I was going to start out lesson 5 by showing you a video called The 3 Incorrect Laws of Motion. We watched it last class.
No, I didn't see it.
That's you're too bad for being away. Still worth being here when you can. So, lesson 5 is entitled Many Body Problems. That's the fancy way of saying, hey, what if you got more than one mass tied together by strings? So in these problems, we have several objects connected together by strings, which at first may seem really, really intimidating. Actually, it's not bad at all. Turns out the easy approach is to realize that we can treat this system as one single object, because if you're tied together with a string, you're accelerating at the same rate. Look up. Here's one mass, another mass hanging. It's impossible for this mass to accelerate at a different rate from this mass. Different direction, yes, but not a different rate. Unless I do this, we're not going to do that. So we're not jerking on the rope. We're going to have smooth acceleration. So if this accelerates at 3 meters per second squared to the right, that's accelerating up at 3 meters per second squared. Why is that so handy? What we're going to do then is we're going to treat this as a single solitary mass. Watch. Example 1 says, find the acceleration and find the string tension. And by the string tension, we mean right between these 2 masses, how hard is that string under strain? Okay. Friction or not? And how can you tell in number 1? Look at the diagram. Hello, friction or not?
No.
No, why? Mu is 0, frictionless. We'll introduce friction later on, certainly in Physics 12. I wasn't planning on introducing it this year in Physics 11, but I might. Next week, we'll see. Okay. What are we going to do then? We're going to do a free body diagram. Although, because there's more than one mass, and they gave me a lovely picture, Emma, rather than redraw everything with a dot, I'm actually going to label the forces right on this diagram. Show you what I mean. See that 3 kilogram mass? What are the forces on it? Get the obvious one. Okay. So what I'm going to do then is, I wrote down here the solution, treat the system as a single object and write a force equation. So I'm going to go like this. But now I'm going to go M1G. Since there's more than one mass, I will always label my masses from left to right. The first one will be M1, the next one will be M2, the third one will be M3, etc. You don't have to do it that way, but Zach, if you want your diagrams to look like mine, that's just the way I go. Is mass 1 sinking into the ground like quicksand? No. Is it lifting into the air like Superman? No. You know what? There has to be a normal force, number 1, that's canceling out gravity, number 1. What else? Friction? No. What else? Hey, which way is this? Look at this picture. Which way is mass 1 accelerating, do you think? I heard someone say it. To the left? No. To the right. So there has to be a force to the right. What's accelerating it to the right? Not the 20, because the 20 is not touching mass 1. 20 is touching mass 2. What's touching mass 1? This piece of what? Piece of string. You know what's tension? Those are the 3 forces on mass 1. Oh, if there was friction, we'd have one more force pointing to the left. It'd be friction force 1, mu times the normal force 4. We can deal with it. Let's move to mass 2. What are the forces acting on it? Get the obvious one. Yep. What else? Yep, because it's not sinking into the ground like quicksand or lifting into the air like Superman. I'll call that normal force number 2. What else? Well, this 20 Newton here, this is the applied force. What else? There is one more force. Turns out, just as the same way that mass 1 is being pulled forwards by tension, mass 2 is being pulled backwards by tension. Why? Because those forces come in pairs. Because that's looking, we have 2 different masses. Well, it's also saying, oh, I can feel you slowing me down as I'm pulling forwards, the same way as you try and tug somebody. Now what? I said our strategy is going to be to treat this as one mass. First of all, can you see vertically everything's balanced and cancels out? So we could write vertical force equations. Meh. They would be M1G equals Fn1 and M2G equals Fm2, whatever. Horizontally, who's winning? If you had to make a guess, who's winning? The applied force, which is in which direction? Pointing to the? So I'm going to go winner minus loser with many forces this time, and anything to the right is going to be a winner plus. Anything to the left is going to be a loser minus. And I'm going to walk down the entire system, down the entire rope. So you ready? Here we go. Winner. Now we walk along, walk along, walk along. I don't care about these 2, they're vertical. Oh, tension. What direction is it pointing? Loser. Oh, tension. What direction is it pointing? Winner. Have we covered all the forces in the horizontal direction? Equals, now here's the adjustment. Up until now, we've always said MA. Do you notice, though, we looked at more than one mass? We took forces from more than one mass. It's going to be M of both of them times A. It's going to be M1 plus M2 times A. That's today's lesson. We're going to practice it, Emma. But as it turns out, if you give me more than one mass, I pretend you didn't. On the right-hand side, instead of MA, it's going to be the mass of all of them times A. On the left-hand side, I just list every force running along the string. Winner and loser, winner and loser, winner and loser. By the way, what's negative tension plus tension? Do you know why I'm smiling? Because I just lost some tension. Oh, you'll get tired of that joke too. I'd like to find the acceleration. How would I get the acceleration by itself? Divide by what? The mass of both. So if I hear you correctly, by the way, look at this. One line, and we're already at our final answer approach. It's why I kind of like the tug of war approach. There is a way to do this, by the way, Trish, using systems of equations, where you write two equations for everything. It's more flexible, but it's uglier. You use it in first-year university physics. I figured then you'll be able to handle it. So I heard you say it's going to be the applied force divided by mass of both. All right, what's the applied force as a number? How big? 20 divided by 3 plus 2, the mass of both of them. And if you had wanted to, Jeff, this one you could have added in your head and just written a 5 there, but often it'll be yucky decimals. But mass of both. Only mistake, sometimes I see kids for some reason multiply the masses together. No, mass of both would be add them together. Anthony, in your head, what is 20 divided by 5? Are you telling me, and I guess I should go to 2 sig figs because that looks like all my data has 2 sig figs. Are you telling me this is going to accelerate at 4 meters per second squared? And I was able to do the whole schmear in my head. This question, can you read to me what it said next to example 1, Anthony? Find what? Check. Sorry, and what? So here's our approach. To find the acceleration, we're going to look at the whole thing and treat it as one big Ubermass. To find tension, we go look at individual masses and write equations for individual masses. Show you what I mean. So to find tension, isolate a single mass. Consider the 3 kilogram mass. What were the forces acting on it again? Get the obvious one.
Gravity.
Gravity, right. And you had that, yes? And we had that. I'm ignoring the other one. Let's write an equation just for this. Vertically, still in balance, Rob, yes? Horizontally, who's winning? Who's losing? Trick question. Tension equals, are we looking at both masses this time? So I don't want to write M both. In fact, which mass did I just draw a free body diagram for? Mass 1 or mass 2? M1A. Do I know mass 1? 3. Do I know A? That's why I looked at both masses first to find the acceleration. What was the acceleration? I scrolled in. Was it at 4, Anthony, was it?
Yeah.
Okay. So our strategy is, if you give me many masses, I try and see if I can't, I'd like to find the acceleration of everything by treating it as one. Once I have the acceleration, I can go look at any individual mass you want me to, and I can write an individual force equation for that mass, and I can find whatever forces you want me to find. So in this case, Anthony, let's keep going in our head. It's going to be 3 times 4. What's the tension? 12 newtons. Hey, that's pretty cool, Mr. Dueck, but what if I hadn't looked at the 3 kilogram mass? What if to find tension, I looked at the 2 kilogram mass? Oh, good point. Next page over. For consistency, I wrote, let's check the other mass. All right, what were the forces acting on this guy? Get the obvious one. We call that M2G. Normal force number 2. We had the applied force, and we had tension. Vertically, again, Rob, everything in balance. Horizontally, who's winning? Who's losing? Okay, so now we would go like this. Did we use any forces from mass 3? So should I write equals m both times a? Which mass times a? Let's get the tension by itself again. I think for this one, Dane, it's going to be easier because there's a minus in front of the tension. Plus it to that side. At the same time, minus that to that side. Can I do that one step? Is that okay, folks? We did that with the elevator questions sometimes as well. So I think I get this. F app minus M2A equals T. Or T equals, let's plug in numbers. What was F applied? 20 minus, what was M2? 2. What was A from earlier? Still the same acceleration. In your head, I mean, you could use a calculator, but it's 20 take away 8. What do you get? Is that the same as we got earlier by looking at mass 1? So point being here, Alex, doesn't matter which mass you look at. Which one's correct? Yes? Well, no, Mr. Dueck, which one? You know what? I always try and do whichever has the cleanest equation. I would have picked mass 1 because I would have said, oh, tension's going to be by itself right away. Less chance of a mistake. I probably wouldn't have picked mass 2. Why? Because I am going to have to do some math to get tension by itself. But it's, Trish, kind of reassuring that as it turns out, I got the same answer. What's our strategy again? You give me 2 masses? You haven't. You've really, as far as I'm concerned, given me 1 mass. Okay, there's going to be some tension in between. We can take that, instead of just having them on a, by the way, also, go back to here. What if mu wasn't 0? I'd have a friction pointing that way. I'd have one more loser in the equation. I'd have friction pointing that way. I'd have one more loser in the equation. Friction is what times what? Mu times the normal force. I don't know the normal force. Look, 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 look. I know another force the same size as the normal force. I think what I'd have, Dane, is minus mu mg minus mu mg. This side, the left side, would be uglier, but I'd still divide by the mass of both to get the A by itself. I could find it. It's longer, Michael. It's uglier. I don't know that it's all that much more difficult. We're going to start out with no friction for a while, but deal with it. Hey, let's hang over a cliff. Let's hang over a cliff. So I wrote down here, identify the net force on the system and then find the acceleration and core tensions. What you need to realize, if this is hanging over a cliff, and maybe this is overly common sense, Emma, there's no way this is magically moving to the left and lifting this up. When something hangs over a cliff, it's the thing hanging over a cliff that's dragging stuff down. In other words, I don't need to tell you the direction. Unlike the previous one where I had to give you an applied force with an arrow pointing, I think here the 4 is accelerating down, the 2 is accelerating to the right, because that's how the universe works. You okay with that? So, what does it want us to find? 2 things, acceleration and what? String tensions. We're going to focus on both of them to find the acceleration. Then we'll focus on one of them to find the string tension. This is the job for a free body diagram. Although in any 2-mass question, I will always give you a picture. And so Trish, from now on, in 2-mass and many body problems, because they give us pictures, we're going to be lazy and just label the forces right on here, because I think that's cleaner, even though technically that's not a free body diagram, because technically a free body diagram is when you represent the mass with a little dot and we're actually labeling the masses. But I'm going to call them free body diagrams, okay? So, what are the forces acting on this 2? Get the obvious one. Yes? What else? What's pulling it forward? And don't say the 4 kilogram mass, because technically that's not. What's pulling it forward? The rope tension. Friction? No. I could easily, though, add it later on, or certainly next year, absolutely, I would give you friction in this question, pointing to the left. Those are the 3 forces acting on mass 1, and vertically they cancel out, so I'm going to probably end up ignoring them. Horizontally there's a tension. Let's go look at mass 2. What are the forces acting on the 4? Get the obvious one. What else? Mm-hmm. Is there a normal force? Oh, thank you. Kids go normal force loopy when they first see it. They want to see it everywhere. There would only be a normal force if this was actually sitting on a surface, and I tried to make this clearly look like it's hanging in midair. That's it. Which way did you tell me this thing is going to be accelerating? So who's winning? You just told me. Which one? Okay, M2G. I've just decided, even though last unit we always said down was negative, this is really why we've gone with the tug-of-war approach. It's going to be far more convenient for us to say, down's winning. Okay? And we're going to walk all the way along the rope, getting any forces. Now that means that any force that ends up pointing down is going to be winner plus. Any force that ends up pointing up, once it turns the corner, is going to be loser minus. My equation is going to look like this. So let's start here. You said winner. The next force I run into is tension. Winner or loser? Loser. Walk along the rope, turn the corner. See, this tension here is to the right, which traditionally was positive, and you might be tempted to think it's a winner. But follow it, follow it, follow it, follow it. When it turns the corner and gets down here, which way will it be pointing? Winner. Right? What about these vertical forces? No, they're not along the rope. I'm going to ignore them. They cancel each other out. This is my equation. Equals. Have I taken forces from more than one mass? On the left-hand side, are there forces from more than one mass? Then I better have M both times A. Why am I so relaxed? Oh, I'm losing tension, baby. I like that. What was the first thing this question wanted us to find? Oh, how would I get the A by itself? Sorry? Divide by mass both? Really? You mean, are you telling me this complicated looking question, 2 lines? Like that. It's going to be 4 times 9.8 divided by 6. You okay with, Trish, I went 2 plus 4 in my head? Okay. Now, this kind of bugs students because they're like, well, Mr. Dueck, wait a minute. How come this isn't exerting a force? This 2 kilogram is slowing this whole thing down because it does appear down there. It makes the bottom of the fraction bigger. It does make your overall acceleration smaller. It does act like a brake, but it acts like a brake because of inertia, because of its mass, not because it's applying a force. Okay, Mr. Dueck, do this one. I don't know. I was going to say do this one in your head. 4 times 9.8 divided by 6. 6.53333. 6.5. How many sig figs? 3 sig figs. It looks like 6.53. Units. It's acceleration. Okay. By the way, it looks like I had solution to. Oh yeah, we're going to be good here. We're okay. What was the next thing? I said find the acceleration, and then what? Cord tension. Looks like I got room here. Let's do the 2 kilogram mass. To find tension, we look at 1 mass. So remember the 2 kilogram? What were the forces acting on it? I'm pretty sure we had M1G, normal force number 1, and tension, and that was it. Hey, Manny, this is a trick question. Who's winning? Tension, because vertically they cancel each other out. So who's winning? You're right. Say it again. Who's losing? Trick question. No one. So are you saying it's going to be tension equals now? Have I looked at both masses? Do I want to write M both A this time? No. This time I want to write M1A. And you realize we're done. Do I know mass 1? 2. Do I know A? Just figured it out. Right? It's going to be 2 times, what was it, 6.53333? And I still have that number stored on my calculator. And I get 13.1. Units, this one is a force. Newtons. Newtons. Hey, you know what? Let's do our consistency check. Let's check the other mass and see if we get the same thing. So, just for practice, what were the forces on the other mass? We had M2G and what else? Tension. Who was winning? And we're just looking at M2. I think we would go, oh, hey, plus that to that side, make it positive. Are you spotting a bit of a pattern, a bit of a repetition, a bit of a trend? I hope. Move that to that side. And I think you would get this. M2G minus M2A equals tension. Let's just check. Does that work? I've scrolled down. What was mass 2? 4? Was it?
Yeah.
Okay. 4 times 9.8 minus 4 times 5 what was it? 5.63333? Or what was it?
6.5.
Oh, 6.533. I'll just add a few extra 3s. Do I also get 13.1? Yep. So on the test, pick the easiest way to find tension. I would have used the first mass because you can see the equation's clear. But you got time before you hand the test in, go find tension using the other mass. You got a built-in error check. And if you don't get the same answer, you've probably done something sloppy. But if you get the same answer, you know you're right. Yay. For problems that involve friction, we can still use the system approach to find acceleration. The tension calculations are a bit trickier because you have to make sure that you have friction in the right place. And you sometimes may have guessed the wrong winner. And if you've guessed the wrong winner, you have friction pointing wrong. And I wrote down here, we'll do this in Physics 12. I've been thinking for a few days. We may do this in Physics 11. We'll see. Moving on. The Atwood machine. The Atwood machine is a pulley system as seen below. You want to know what an Atwood machine is? This is sort of an Atwood machine where you have 2 masses on a rope and a pulley. The only problem is this isn't a really good pulley. You see, the pulley has to be magic. We're in our magic physics world again. The pulley is massless and frictionless to make the math easy. Oh, and you know how much the ropes weigh? Nothing. To make the math easy. Because otherwise, technically, there's more rope here than here. You could make an argument that it would get pulled. So what's the Atwood machine? It's where you have one mass hanging from a pulley, a rope going through the pulley to another mass, and mass 2 is called the counterweight. It makes it much easier for a person or a motor to lift mass 1. Almost every elevator looks like this. Almost every elevator has a counterweight equal to the empty elevator car, so that all the electric motor has to lift is the people or the cargo of the elevator. It's not having to actually lift the mass of the car itself. It's a much smarter way to do it. It's a much more efficient way to do it. Also leads to some nice physics. So here's our first thought experiment. Suppose that equal masses are placed on both sides of the Atwood machine, and one mass is lifted higher. When you release it, how does the system move? So these are equal masses. Now this is not massless and frictionless. These are equal masses. We start out like this, and then we're going to lift, which side is it for you guys? That side. We're going to lift one mass higher. When we let go, what will happen? Nothing. The higher mass wants to fall down, or the lower mass wants to fall higher. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. Don't make fun of me, Mr. Dueck. Okay. Ready? Who says, Dueck, A, the system's going to remain at rest? Who says, B, Mr. Dueck, the higher mass wants to fall down? Who says, Mr. Dueck, the higher mass is going to go higher? This is a job for a good free body diagram. Or you know what? Let's label our forces, okay? So the masses, it says, are equal, right? So here's a lovely picture. Let me zoom in. Let's call this mass 1. Let's call this, oh, are the masses equal? Then let's call this mass 1. What are the forces acting on the left-hand side? Get the obvious one. Absolutely. Is it in free fall? What else is attached to it? Tension. And that's it. What are the forces acting on the right-hand mass? Get the obvious one. What else? Tension. Now, you folks said that the higher mass goes higher. So if the higher mass goes higher, what's the winning force here? I think you guys are saying that that's winning. Is that right? So let's let that be a winner. Let's write an equation. Winner. So anything, when you come all the way around, that ends up pointing down is going to be winner. Anything that ends up pointing up is going to be loser. So this tension here, winner or loser? You just said that this is winner, right, Darian?
Oh, yes, sir. I got myself.
So winner or loser? Loser minus. And by the way, you might be tempted to say that this tension is also pointing up, and so it's a loser. But follow it around. Follow it around. When it gets to this side, which way does it end up pointing? Down, winner. And you might be tempted to say that this left-hand mg here is actually a winner because it's pointing down. But follow it around, follow it around. When it gets to this side, which way is it pointing? Up. Loser. And we've looked at the masses from more than one, forces from more than one mass. What? You're saying that not only am I relaxed because I'm losing tension, you're saying, oh, if everything cancels as a number, what's left on the left-hand side? Okay, how would I get the A by itself? Come on, don't freeze on me. How would I get the A by itself? Divide by the mass of both. So the acceleration is going to be 0 divided by get your count. What's 0 divided by 5? What's 0 divided by 10? What's 0 divided by anything? Technically anything except 0 itself, so we're ignoring it. So if we divide by the mass of, but what is the acceleration here? We've just proved that it has to be. So does anybody want to revise their guess? Atla, what's the correct answer, do you think? A. It has to remain at rest. Why? Because it can't accelerate. Or it could keep going at a steady speed somehow, but that wasn't an option to pick from. Emma, have I convinced you? Okay. It says, using principles of physics, explain your answer. There. Those of you that take Physics 12, it turns out on the old Physics 12 provincial exams, which is sort of what I still base my tests on, there were actual essay questions like this. And by essay questions, I mean they would give you some kind of a situation and say, prove it. I can't say I answered this in English, I answered this using physics, but they loved to give you, hey, prove it, prove it. So I'm trying to throw some in Physics 11 so that those of you that do take Physics 12 next year, you're not so terrified by them. This was a classic one. And a lot of kids obviously initially get this wrong. Have I convinced you though? Can you see why you were guessing wrong, right? You were confusing velocity, distance, and acceleration. Hey, that's happened earlier today. And don't feel bad, that's a tough thing. Michael?
If the string had mass, then it would...
If instead of string it was chain? Yep. Yep. And that's why I said this is a magic. The Atwood machine it's an idealized machine. The pulley itself has no mass or friction, and the rope has no mass or friction. Otherwise, the math, in all honesty, gets yucky. If you actually had string with changing mass, yeah, you can only solve it with calculus, because the mass would be constantly changing. Anytime you have something that's constantly changing, that's what calculus was invented to designed to solve. Let's go like this. Okay. Work on your take-home quiz for sure, and then also if you haven't finished the homework from lesson 4, work on that. We're going to pick up with this next class, multi-mass problems.